Sorry, it happened again. Now I'm a little worried it's going to keep happening.
If it happens again, it might be a good idea to just record the lecture so we can watch it later.
Yeah, we're not going to waste a lot of time here. I'll try actually just doing it straight through my iPad if it happens again, instead of iPad and computer. But yeah, we don't want to waste our time. So the pattern we're going to see here is kind of the same thing. In other words, let's go do this right now. Let's go right at the vertical version. Stick with black. Try to make this as clear as I can. So what about the vertical, or the kind of the Y version of this? What would its equation look like? Well, again, it's no different. It's just going to be our AB equation except for Y, and our AC except for Y, and our A of B with respect to CT, but only in the Y direction. And so the black equations, actually, do you see it as 2 equations, 8 unknowns? I mean, this is not good. The black equations are 2 equations, 8 unknowns right now. But notice I can start to diminish that, because what I really need is 2 equations, 2 unknowns, or maybe 4 equations, 4 unknowns or something, but I can't do 2 equations with 8 unknowns. And so that's kind of the goal. So the question is, could I rewrite these in a way that makes this a little nicer? Well, take a look up here at this acceleration of B with respect to T. Well, notice it is at an angle. Question is, what angle is it at? I won't belabor this point much, but to say that if you think about it a bit, that's actually going to be 34 degrees as well. If this is 34, this would be 34. And since that red angle is 90, then that means this angle would be 56 degrees. And then 56 and 34 have to make 90. So that's how it worked its way up there. So that's at a 34-degree angle as a direct result of the bottom being at a 34-degree angle. So the question is, does it make sense I could modify that? In other words, I don't have to say with respect to X here. I could just say that this is the acceleration of B with respect to C tangential without the X by just modifying that answer times the cosine of 34, since cosine would be the X component. Do you agree with that? So now it doesn't have the X anymore. And then do you also see, because I decided to let the coordinate axes work, that that's also aiming left. So I guess I should throw a negative in front of that. Do you see that down here, I'm going to be able to do the same thing? That's kind of the idea. I could say, well, this is also just the acceleration of B with respect to C tangential, except for it'd be modified by the sine of 34. Do you see how that just got rid of one of the variables? Instead of a TX and a TY, now I just have BCT, BCT. That just combined them. I'm using one variable now. So I'm making inroads in my 2 equations, 8 unknowns problem.
Also, the acceleration of B and the Y, it would, because of how we're oriented, would just be the normal acceleration of B, right?
Good question. No, they're not the same. They're not the same answer, but it is going in the same direction. And notice that would be up. So this would be positive because it's going up. So it is fighting against, it's going up, and then ABN is going down. That's what you're referring to. It's over here going down. So one's going up, one's going down, but they're being controlled by 2 different things. So they're not exactly the same, no. But they are going in the same direction now. And that's what we wanted, because we wanted a vertical equation out of this. So let's go see if we can do the same thing with the other one. So since this angle, looks like we need this after all, since this angle is 56 right here, then isn't our normal acceleration also modified by 56 degrees? again, that's not the only angle that I could pick, but can't I then come down here and do the same thing and say, well, I don't have to write this with an X in it. I can say that's the same as the acceleration of B with respect to C normal, but to limit it to the X direction, I would have to take the cosine of 56. And again, that is aiming left. And so if I'm going to use signs, I'm going to have to call that one negative as well. And the same thing will be true for this second one, except for, of course, it will be sine of 56. Acceleration of B with respect to C normal modified by the sine of 56. And notice it's going down. That's going down. So I'm going to have to call that one negative as well. So the black equations, I had two equations with 8 unknowns. We're making inroads. Before I recount them though, let's go take a look at these last two right over here. Is there any way I could rewrite those based on what I know?
Well, we were provided with the acceleration of C, and it's going in the y direction. So
Exactly. Acceleration of C is going in the y direction, so I get to replace that one with just a 2. And again, I'm calling down negative, so I guess I'm gonna have to call that negative. What about acceleration of B in the y direction? Well, that's kind of similar, since acceleration up here in red was horizontally acceleration of B tangential, and the vertical version is normal, then I guess I could replace it just like I did above with acceleration of B with respect to N normal, which again is downward. So I guess I'd have to call that negative. So I've put in everything I can put in. So I'll record it this way. In black, I had 2 equations, 8 unknowns. But now that I'm in green, what do I have? I still have 2 equations, but how many unknowns am I down to? What do you get?
Two.
I'm seeing acceleration of BT, acceleration of BN. That's a bummer because those are not the same. And then I got BCT, BCT. So at least that's a repeat. And then BCN and BCN. So, and that's a repeat. I'm seeing 4. So that's progress. However, we're not done. So that's not good. So I'm going to need some more help. What are your thoughts?
the first thing that comes to mind is that if you're in a situation where just looking at a much simpler situation where we just have something moving in a circle, then we know that the normal acceleration is proportional to the velocity it's moving around the circle. But it's a lot more going on here.
Yeah, so this is a little bit more complicated, but here's kind of where, so it's a good thought. But here's kind of what I said a second ago comes in. In other words, this business right here, in other words, can I replace those normal accelerations? Really, I'm just looking at the normal ones. The normal ones, does it make sense what this equation is saying right here is that if you knew the velocities, then you would actually know the normal accelerations. Does that make sense? In other words, we're gonna go this direction. So I'm saying I got 4 unknowns, but we have the tools to figure velocity out from last week. And so if I did that, then I would not have variables for my normal accelerations. Does that make sense? So if I didn't have variables for my normal accelerations, that means this one would turn into a number that I know that's normal. And this is the same one. So these two would be numbers now. I would actually know what those are as numbers. So that got rid of one of those unknowns. And then this is a normal one over here. So that's how I'm going to basically get 2 more equations is what it comes down to. I'm going to have 4 equations, 4 unknowns, depending on how you look at this. And so we said that acceleration normal was actually equal to the velocity squared divided by the radius. So what does that mean to us? Well, it means a couple of things, because I got 2. I got acceleration b normal. So that means I need the velocity of b, which I can square, divided by what?
Radius.
Which radius? Because I have 2 radiuses here.
It wouldn't be the radius of BA. So the normal acceleration.
Yeah, exactly right. In other words, this velocity normal right here, or that normal right there, goes with the radius AB, and the radius AB is, given. That's 1.5. So I'm going to write the radius of AB here, but I'm even going to kind of take it out right now, just so that it's. So if I can find the velocity at B, then I'll be able to square it, divide by 1.5, and then I can I'll be able to replace that with a number. That'll be cool. And then secondly, what about the acceleration of B with respect to C in the normal direction? Well, that's no different. It's the velocity of B with respect to C, then I will square it, and then I'll be dividing by the radius of B with respect to C, or the radius of BC. And we saw up here that the radius of BC was given. It was 5.8, so I might as well throw that in right now so my brain doesn't hurt. And so whatever number I get for that, then I'm going to be able to throw it both here and up in the location above that. And so that'll get me to 2 equations, 2 unknowns when I make that substitution. So you can think of this as all combined now. I have 4 equations, 4 unknowns. Or you can think of it as soon as I make those substitutions, I'll finally get it down to 2 equations, 2 unknowns. It's kind of up to you. For the sake of the model here, I think I'm going to go to purple, and I'm going to say this right here is equation 1. I'm not going to redraw it nicely. I will on the next page. That's equation 1. This is equation 2. This is going to be equation 3. And that is going to be equation 4. So eventually I want to rewrite all of those equations, but this is just a lot to keep straight. So let's go hunt for velocity of B and the velocity of B with respect to C then. Let's go hunt for those. And just for the sake of practice, let's try to do this with the with the ICR technique. So let's see, is that going to destroy the picture that I have up here, or can I get that into the same picture? That's the question. I think I can get it into the same.
It doesn't look that bad, I think.
So do you understand that I'm staring at the velocity of B and I'm saying, okay, what center around is that rotating around? Well, it's rotating around A permanently, but what is it rotating around instantaneously? Well, remember, it's perpendicular to that. So basically it could be anywhere along this line. And what I'm after is a point that works for both. And then, so that's where B is going. Well, where is C going? Well, C is aiming straight down. And so it's also could be considered to be rotating around a center. So do you see that I'm doing the same thing there? It's like, where is C going? Well, C is, if I'm thinking of C, at least instantaneously, C isn't rotating. It's not going in a circle. It's going in a straight line. But at least for this instant, given that it's right there, its radius would be located on a line perpendicular to the direction of travel. So up here, I've got B traveling this way. So its center would have to be on a perpendicular. I got C traveling this way. Its center would have to be on a perpendicular. So that means that is the instantaneous center of rotation right there, which is really nice, because what kind of a triangle is that?
A right triangle.
It's already a right triangle, which means I don't have to do law of sines and law of cosines to find those two radiuses. So I need to know the velocity of BC and I need to know the velocity of B. So this is going to let me get the velocity of B. That's kind of what this comes down to. Let's see, what do I know in this picture? Well, I was told that BC was 5.8. So basically it means I know the hypotenuse of this triangle. I know it's a right triangle. What else do I know? Well, that 34 degrees means this angle right here is 56 degrees, or this angle up here is 34 degrees, whichever I want. And I know one side. And so I know a length, I know an angle, I got regular trigonometry. So cosine of 56 would be adjacent over hypotenuse. So that'd be 5.8 times the cosine of 56 degrees, which comes out to be 3.24. So this distance is really 3.24. And then sine of 56 would be the opposite over 5.8. So if I take 5.8 times the sine of 56, I get 4.81 approximately for that. And I don't know, maybe I don't need this, but these are in meters. And so how do I use that to connect? What's the concept here? Because again, I'm interested in what part of this persists for you a lot further than just through this next test, because it's the thinking that will persist. The details, you're going to lose them. But why is it cool that we found one center that handles both of them at the same time?
Because then we can find the shit, what's the term? I know the symbol, I can't remember the term. The crap.
Yeah.
The omega of both of them at the same time.
Yeah, that's exactly right. Their omega, which is their rotational speeds, are identical at that point in time. So whatever their rotational speeds are, they're identical. So I could say CI, the rotational speed of C as it rotates around I will match the rotational speed omega, angular velocity is kind of the other way to say it, of B as it rotates around I. Those are going to be identical to each other, since I have one center that applies to both of them. And since, if I remember right, we said that the linear speed is modified by taking the rotational speed times R, then that means I could just replace these. If I solve that for omega, it'd be V over R. So that means I can take V of C and divide it by the radius that goes with it. And that would have to be equal to the velocity of B divided by the radius that goes with it. And of course, that radius in this case would be CI and BI. Well, that's what's so cool about this. It kind of sets up this proportion, and I actually know 3 of those 4 things. I know the velocity of C, which was given, was 5. And we just figured out that the radius of C was 3.24. We don't know the velocity of B, but we did figure out the radius of B is longer, 4.81, matches the picture. Hence, I can say I know now the velocity of B. Let's see, what is it? 4.81 times 5 divided by 3.24. I'm getting 7.42. So that's cool because now if you look back over here, I'll write this down a little more formally later, but now that I know that, does it make sense? I can go back to this third equation here and I can square that number and divide by 1.5 and I'll now know that means that acceleration of B normal is no longer a variable. That's cool. But the problem is, what about the other one? How am I supposed to get the other one? Like, what's the method to get that second one? How am I supposed to get that? What's the velocity of B as it rotates around C? How am I supposed to get that? Who knows? Well, remember, that was the problem in the first place. In other words, when we look at this, we say, we know the velocity of C is moving at 5, and it's related to the velocity of B and B with respect to C. But we basically said, if you want to know what's happening up at B, then you say, well, it's exactly the same as what's happening at A, plus that rotation of B as it rotates around C. This is wrong. What's wrong with this? B as it rotates around C. What's wrong is that was a C. If that was our basic equation that governed the relationship of all of these things. So we know the velocity at C, that was given to be 5. We just calced the velocity of B to be 7.42. And so that's going to allow me to find the velocity of B as it rotates around C, which apparently is 2. I'm a little concerned that negative numbers, do I need to think about negative numbers? Do I need to think about X's and Y's here?
I think so.
Is that too simplified? Do I got to go back and look at X's and Y's in order to make this work?
I think one of the velocity of B or velocity of C has to be 0.
Yeah, this sort of feels like maybe I'm getting a little ahead of myself. Let's see in this case if I need to be a little more careful. So horizontally in X, velocity of B in X equals velocity of C in X plus velocity of B with respect to C in X. Vertically, velocity of B in Y equals velocity of C in Y plus velocity of B with respect to C in Y. So do I need to consider those separately? I think I do. That's kind of tricky. So let's see, what do we know? Well, we know the velocity of C in X, because it isn't allowed to move in X, is 0, whereas the velocity of C in Y, it's moving straight down, is 2. I'm sorry, 5. It's 5, except it is moving down, so that'd be -5. Remember, as soon as I switch to X's and Y's, there are such a thing as positives and negatives. But remember, when stuff is moving rotationally, positive is in the direction it's traveling. So the negative coordinate axis only applies with X's and Y's. So, okay, that's cool. I know that. And then, well, this velocity of B over here is 7.42, but notice it's horizontal. I didn't have to modify it. It is horizontal. So that 7.42 is only in the X direction. So that is X. So velocity of B in X, that is -7.42. So that means I'm going to be able to find the velocity of B in the X direction. Velocity of B in the Y direction? Isn't that nothing? So again, notice something interesting. This allows you to find separately the velocity of B, C, and X and the velocity of B, C, and Y. And then I could do the Pythagorean theorem on that to just get the velocity of B with respect to C. But remember in the picture, I could just replace these. The velocity of B with respect to C, I'm looking back up here. Velocity of B with respect to C is pointing in that direction, but remember it can be modified by 34 degrees. So probably a better way to write this is to replace this, like replace this with just the velocity of B with respect to C, but modified, since it was an X, modified by the cosine of 34 degrees. Now, again, should I apply my own negative sign to this because I see that it's left? I think the answer to that should be yes. I think I should do that. And down here, similarly, I could say, hey, that's also the same as the velocity of B as it rotates around C, but that would be a modification of the sine of 34 degrees. And that is going up, so it would be positive. So apparently I'm going to get the same answer from both of these. Is that true? So if I take for the top equation, if I take 7.42 and I divide by the cosine of 34, I get 8.95. If I take 5 and I divide by the sine of 34, I get 8.95. There's a little bit of a rounding issue there. I got 8.95 and 8.94, but yeah, basically that's the case. Another option to this would have been just to say, hey, that's the same as the velocity of B. But again, we already calced that. We just happened to have already calced that earlier. That's the thing that's interesting. So if I did it that way, I would have looked at the top one and said, oh, that's too bad. It still has two unknowns. If I started with this, notice if I had started with this and I didn't even do this business up here, this is kind of interesting. If I'd have just started with this down here and skipped all of that rotational business, notice I could have gotten this question right just from here. So I would have sort of went to this one and discovered that the velocity of B with respect to C is about 8.95. And then I would have secondly thrown it in up here and then found that the velocity of B is 7.42, but it would have so in our case, we just kind of, I don't know, thought a little more deeply and did it all at once. But it agrees, everything agrees. That's kind of good. So just to give you time to process a bit and kind of make sure you're sort of seeing the big picture, because this, as I said, is so confusing. If I go back to my equations, I had my first equation, which was this guy, which I'm going to drag down here just so I can make a good copy of it so I can see it. So that was negative acceleration of B tangential equals 0 minus acceleration of B with respect to C tangential times the cosine of 34 minus acceleration of B with respect to C normal times the cosine of 56. So that was our first equation. Awesome. Second equation was the same thing, except for the one that came from the y direction. But notice there's no remnant of the x's and y's here anymore, because we've got cosines involved to kind of produce that or take care of that. That's why we have less unknowns. So if I steal, though, the y equation, negative acceleration b normal is equal to -2 plus acceleration of b with respect to c tangential modified by the sine of 34 minus acceleration of b with respect to c normal times the sine of 56 . And then these last two equations down here, 3 and 4. What was 3? Let's just grab both of these at the same time. Add those to the mix. So our third equation, you don't need to write it this way. It doesn't matter how you do it. You could just write those two equations and go throw your conclusions into those and just get it down to 2 equations, 2 unknowns. I just think it's kind of cool to include it this way. So acceleration of b normal can be found by taking the velocity of b and squaring that divided by 1.5. But we know what the velocity of b is. We just figured it out. It was 7.42. So I'm going to just replace it rather than cross it out. 7.42. And I think I'll just write it over here. The fourth equation that we had was acceleration of b with respect to c normal is equal to velocity of BC, which we said was 8.95. So 8.95 squared divided by its radius, which was 5.8. So the way I chose to write this, I now have the happy result of 4 equations with 4 unknowns. And so algebraically, I can finally solve that. So let's see if we can do that. So 7.42, after you turn your calculator on, 7.42 squared divided by 1.5 is 36. Notice I rounded 7.2 and now I'm rounding this yet again. So I'm going to be off a bit. I know that and I don't care. I'm just trying to get the idea. 8.95 squared. This one works out to be 13.81. So of course, that's what I'm going to do now. I'm going to take my 4 equations, 4 unknowns, and I'm going to sub in 36.7 right there for ABN. That's the only representation of that I have. 13.81 goes 2 different places. It goes here and it goes here. So I finally only have 2 equations with 2 unknowns. And if you notice, the second equation now only has 1 unknown in it. That's pretty cool. So let's see if I add 2. I've got negative 36.7 over there, negative 36.7. If I add 2 to the other side and I add 13.81 to the other side, I got negative 20.89. So this is negative 20.89. 9 equals acceleration of B with respect to C tangential sine of 34. So I just need to divide by the sine of 34, divided by the sine of 34, and I get negative 37.35. Something feels wrong about that. Oh yeah, I never multiplied by the sine of 56 over here, so I gotta redo that. So negative 36.7. I can add 2, but then I've got to add 13.81 times the cosine of 56, which is a very different number. So I get negative 26.98 here instead. And it's that I need to divide by the sine of 34. Yeah, I like making these mistakes public. I was looking at the top equation when I did this, so I should have been multiplying by the sine of 56 here, so that's not right. So it's negative 36.7, just to reiterate, negative 36.7 plus 2 plus 13.81 times the sine of 56. So easy to do dumb things here. So I got negative 23.25. And if I divide that by the sine of 34, I think I finally didn't screw this up. So I got acceleration of B with respect to C tangential being approximately 41.58. And notice that's a tangential or a speed acceleration. So that's meters per second squared. So that feels like an answer. I've sort of forgot what I was even trying to calculate now. Now that top equation, number 1, has, well, unknowns in it, 2 unknowns in it, but now I know one of them. So instead of the top equation having 2 unknowns in it, now it just has 1. Negative acceleration of BT is still an unknown. But I just figured out the acceleration of B with respect to T. Now here's where the sine thing comes into play. And I get a little confused by this. That's the downside of my approach. In other words, I got a negative number for this, but do I throw it back in up here and then a negative times a negative is a positive, it becomes a positive number? I find myself going, uh-oh, I'm not sure. So that's that first equation up here. Let's see what I get. So if I throw that all in, I get negative acceleration of B with respect to T equals, and on the other side is actually a positive number. So that actually leaves acceleration of B tangential to be negative 26.75. Also meters per second squared. So am I done? Is that what this question was asking? Well, I hope so, but let's go back and see because I kind of forgot. I just sort of figured out everything. Remember, I guess the one thing I'd like you to take away from this is as soon as I wrote those two black equations down right there, as soon as I wrote those two down, it just became algebra from then on. And it's very complicated and I can absolutely get lost as a result of that. But it just became, how do I solve two equations, 8 unknowns? That's the majority of this problem. And I just continued that until I found all the answers. And now for the first time, I'm going back and saying, am I done? And I see that, oh, darn, I guess I'm not. I wanted to know the angular acceleration of BC and the acceleration of B. So let's start with the angular acceleration BC. How do I get that from what I just found, since I guess I'm disappointed to find I'm not done? So again, I'm thinking back to those formulas we had earlier. So I'm trying to find this. And I'm remembering that acceleration was equal to angular acceleration multiplied by the radius of it. So if that's true, then this acceleration, which is the acceleration of B, it's acceleration of BC, since that's what I'm working on here. Well, that I know. And notice this was a speed thing. Like this wouldn't work if this was normal, but I'm referring to this up here. In other words, that's the negative 41.58. Because this pertained to tangential, like speed change version of acceleration. And the radius of BC was something I knew, that was 5.8. So turns out I'm dividing those. If I divide 41.85, 5 divided by 5.8, I actually get 7.2, and there it's negative, so I get angular acceleration is negative 7.2. What would the units for that be if you were pressed to it? How are angles measured? It'd be kind of cool to leave the units in this if I put meters per second squared here, and this was meters, then I'm dividing meters per second squared by meters, which means the meters cancel and I get nothings per second squared. So this is radians, like that's what a radian is. It is a unitless number. It's a unitless unit. Whew. So that's actually the answer I was asked for. What was the other answer I was asked for? The acceleration of B, just the acceleration of B itself. Well, I have the acceleration of B tangential. And I have the acceleration of B normal. So acceleration of B normal, we said back here was 7.42 squared over 1.5, which is 36.7. So I have that. And I have the acceleration of B tangential, which we just figured out a second ago is negative 26.75. What do I do with those? Or, you know, what is it asking? I mean, is it, again, I find this a bit of a confusing question because, you know, what does acceleration of B mean? Speed change version is tangential. In my opinion, the best answer for this is just There it is. There you go. You're done. Could we add those as vectors potentially and sort of, write it in another way? I'd say, well, yeah, I suppose we could.
Seems a little pointless.
I agree. That's exactly why I think we're done. In a sense, I'd say we already found that. We found that earlier. Better to keep separate. Well, how about that? We started at 11. It took us an hour and 20 minutes to do one problem. It's terrifying. So I guess both of these are in. Interesting. So given that, I think what I would like to do is on Thursday, look at this question, which is a real similar modification, but just because I think it's going to help to see this maybe more than one time. Notice this time the driver cylinder is actually moving to the left, which is still going to cause this to kind of rotate in that direction. But this is now sitting in some weird angle. It's like some random location. So the question is, can I still kind of survive that? So it's going to take two angles now to describe where everything is at our snapshot in time. But notice the problem is kind of the same. And so I think just trying to sort that out, maybe one more time. I can do one more example. So anyway, let's plan on doing that Thursday. You can attempt, what I'd recommend you do is stare long at this process right here, because it took 3 pages to kind of pull that off, 3.5. See if you can kind of assimilate any of this. Man. Because obviously your capacity to repeat this, in the end, notice this one question is kind of the culmination of everything we've studied in this chapter. In the sense that notice we had to do all the velocity questions from last week. We had to do those as part of trying to get today's question right. So with respect to what you're going to see on the final or in the last test, notice I'm really only going to be able to, it took us an hour and 20 minutes, and that's me knowing what I'm doing, if you will. So when you're taking a test, you might feel that sort of sense of need to think. So my only thing I'm going to probably do on the test is, rather than just say solve this problem, it might be nice to ask you this question first. Does that make sense? So on the test, I might give you the drawing kind of without this acceleration. And just say, all right, go find the velocity at B. Go find out what's going on up there. What's the velocity at B? And what's the velocity at B as it rotates around C? So, do this part of our problem right here and get an answer for it, and you're all done. Cool. You get a bunch of points for that question. And then the second question, I'll say, okay, great. Now let's give this a 2 meter per second acceleration, in which case you start doing these black equations. But then when you need the velocities, you've already got them. Does that make sense? And that'll allow you to make the question feel a little simpler. Maybe we'll do that tomorrow, just as kind of a model. Maybe tomorrow, knowing we're going to need those now, maybe we'll just kind of go do this first. And then we'll have those waiting for us. We'll have these two velocities waiting for us, so that later on when we need them, we'll be able just to kind of plug them in. My process today went from 2 equations, 8 unknowns, down to 2 equations, 4 unknowns, and then I chose to go to 4 equations, 4 unknowns. But if we were sitting here with these 2 equations, and they were asking for some velocities, then I could just plug them right in. I could plug them in immediately. So, all right, go cogitate on that. Say after if you want, but we're at time. So boogie on out of here and we'll see you next time.
All right, bye. I might not see you all Thursday because graduation stuff, but
Oh, cool.
I might.
Sounds good. I'll post it. So no problem.
So is that still fine, me sending you homework 16.6 today?
Absolutely. Yeah.
I'm just gonna solve it real quick. And
Mm,
this
take-
is
Take your time.
16 what is that?
Take your time. Yeah, you're good.
And this is 16.7.
This is 16.7.
Yeah, it's not like that bad, but it's just so many things going on in here.
Yeah. Yeah, it is. It is. It sort of feels like, doesn't it sort of feel like you could understand this and still get it wrong unless you had time to check your work. So the only thing I would say on a test, and you are future engineers here, so work really slowly, carefully, in some organized kind of a fashion. Like I did a pretty good job with that today, but if you stare back at this page, doesn't that look a little confusing even still? So, I'm going to stare at your test without the benefit of this stuff getting written in any kind of an order. So even though I feel like I did a reasonably good job, I look at it now and think I would want to grade that. How am I supposed to grade that? I'll be very concerned when I grade this to take my time and hopefully figure out everything you did, so that if you made some kind of a sign mistake or a calculator pushing mistake, that kind of a thing, that I'll be able to kind of see, oh yeah, that's what happened here, and then I can follow it the rest of the way through. And maybe I find 2 sort of dumb mistakes, and I can determine they're dumb and not as important. So mark it wrong, but not take as many points off.
I actually really like this section. This section is fun.
Yeah, it's really neat, isn't it? I mean, I guess to me it's so neat, as I mentioned before, just because it's this relative motion analysis is so common because there's so many things that are connected to each other in this way. And of course, because it's modeling with a combustion engine, it's something you can appreciate. That's a backbone invention of our culture. And it's also cool that it's so complicated to understand. It seems really simple, but man, it's surprising how much work you have to do to kind of figure out what's going on.
Yeah, one of the big thoughts I've been having so far is that it feels like it'd be a lot easier to just put everything in a matrix.
Yeah, absolutely.
even like relatively early on, display X and Y into 2 different rows, and then just building from there. So I have one question about the 16.7 homework, because I'm kind of curious if my thought process makes sense on this one. So I've got a problem where the I guess instantaneous velocity is basically pointing in the exact same direction.
Okay. Which
Or sorry,
question is this?
the instantaneous, I guess. So like when you're it's 16-111.
111.
Yep.
Got it. Okay.
Yeah. So my first thought with finding velocity for anything is always the instantaneous center, because it's a lot easier.
Yeah.
But how do you apply that if the the theoretical lines you'd be drawing out would never intersect if they're just parallel?
Yeah. I completely get what you're saying there. Huh.
Yeah. So one thought would be, are these,
Well, let's see, let me think about this. I don't think that's actually true, but let me stare at that for just a little bit longer. Hmm. Yeah, that's a terrific question you're asking.
yeah, my thought was, theoretically, would this mean that the, because ordinarily we math it out to find the angular velocity. But here, let me check my notes in 16.6. We usually use the to find the angular velocity, it's the velocity at that point over the length, the I guess technically it's a radius in this particular case. But if these are theoretically not connecting ever, could we treat this as a theoretically infinite length, which means that the actual result would be approaching zero potentially, or is zero for the angular velocity?
That's correct. In other words, you can do exactly what you said. You just have to think of the radiuses as being infinity. That's actually I'm looking at the author's approach to this, and that's exactly what you did.
Okay, well, it's good to know that works, but
yeah, weird.
I don't really want to use it because I don't think I could use it again without checking my notes.
Uh-huh.
All right, well, that's my big question. So
that's a wonderful question.
I'm kind of really glad I saw that, but I feel so weird. I don't like it.
Yeah,
which actually, I don't like it at all.
Which actually means that the rotational speed will be zero. It won't be rotating at all. In other words, angular velocity, rotational speed, angular velocity will actually be zero because you're taking a number and dividing it by infinity.
Yeah. All right. I'll try that on the homework. I'm not sure if I'm gonna like it.
Well, and what's kind of cool about it is that the velocity of A is actually 4. That's given in the problem, and what that's gonna produce is the fact that the velocity of B is identical, because it basically means there is no rotation at that point.
That makes sense.
Just given where
cool.
it is. Yeah, it's really cool.
All right. Well, I'm gonna head out.
Okay.
I've got my big question answered.
Good job.
So after the sections like this, I really want to change my major to like manufacturing engineer. Really design a motor or something like that.
I know. Isn't it kind of neat? It's kind of makes you want to get in there and play around and like produce things of this nature and calculate them and kind of watch it working and start to and then make modifications to it based on all these calculations and
and after see it go, like measure the horsepower and how fast it can spin. So we have like two more weeks. Is that what it is?
Yeah, counting this week.
Okay. All right. So I have to go probably do a bunch of homework for sure.
All right. Good to hang out with you as always.
Yep. Thank you.
See ya.
Yeah.